this is a like a recap of the last lecture. Um, Prior to this lecture, we talked about in detail the spatial coordinate system and the body fit and the material coordinate system. So I'm not putting that here, but what we want to take away is that firstly, there is a material particle which can be defined as a group of atoms which we designate as our particle of interest, and which is what we aim to track. So if you have a material, you select a point in that material and you apply loading in that, let's say the whole sample. You can take any sample, apply loading anywhere in that sample, but you might have a particle or point of interest. You might want to know what happens to this point if I apply a load a little bit adjacent to that or at that point or nearby to that point. So any any group of atoms in that sample can be designated as our material particle, and ultimately we want to know what are the changes in length, area, volume in the vicinity of that particle, or what happens to that group of atoms in which we are interested in. X uppercase is the vector describing the material particle. What does that mean? Can somebody tell me? What is yeah? Dimensions. Sorry, you see, this is not a one-word answer thing. You just randomly say some words and you expect me to get some meaning out of it. You have a sentence, come up with it. Breakups to different particles, it's four or three. It is X can be written as X. You're right. X is the union of points, which were initially which were designated as the material particle. So that droplet example, the droplet could break up into multiple fragments. All of that represents the material. Or you could have a solid material which has been, let's say, squeezed at the middle so that it becomes two lobes connected by a teeny tiny bit of material connecting the two lobes. That still represents one particle. Wherever that particle or that group of atoms exists, that is described by X. The lowercase x, on the other hand, is just a vector describing a point in space. So with respect to some coordinate system, you can designate the point as x. And it's like saying at a given position, there might be a particle, or there might not be a particle, but that position itself has an address or a position vector. That is what the lowercase x is. Most directly saying it, X is basically what you observe from the laboratory frame of reference. Okay. In general, the material particle is a function of position itself. What does this statement mean?
Position of the material particle is going to depend on how you're defining it in the point in space and space.
Okay, it's close but not exactly there. Anybody else wants to try? So you take the droplet example. Okay, suppose you compress the droplet and turn that into two daughter droplets. Initially, wherever the droplet existed was your material particle. Now that has bifurcated into two droplets. Wherever the two droplets exist is your material particle now. But you can at a given moment, you can describe where there is oil in that droplet or where that oil is situated. That where is the small x, is the position. It could change over time. It could change with position. Wherever that oil exists is your uppercase X. Are you able to connect with this example? It is defined as all the positions where which there is a material. Whereas X is just an address for that location. Okay. Um, I gave you the country example. Which all territory a country calls itself as its territory, the country exists there. Today, that territory may not belong to a country, but that is like X. Let's think of, hypothetically speaking, Greenland. Today, Greenland is not part of USA, if you are following the news. So X, which refers to Greenland, is just referring to Greenland. But if Greenland becomes a part of the USA, then if you say, where is USA? You can go to Greenland and say, I'm in USA. So that territory becomes part of that particle, which we call USA, or a country, which we call USA. That makes sense to you? All right. I won't harp on this further. I hope you understood. So when we think of D uppercase X, that is the change in length of the material particle. That is the true change in length. Whereas dx is merely a change in position in the spatial form frame of reference. So when you are looking at it from the experimental the laboratory frame of reference, two points in a material could have moved apart or moved closer. What you observe is where they are in your frame of reference. But in the material, when they change length, that length may not all change in the same direction. There could be lateral compression or lateral changes also, which is included in this dx. So we write dx is the relevant quantity to be calculate length, area, or volume changes in the material particle, and we write x is equal to the deformation mapping as of uppercase X, and the deformation tensor or deformation gradient is defined as partial derivative of xi with respect to xj, which defines the deformation tensor as a mixed order tensor with one basis from the spatial coordinate system and one basis vector from the material coordinate system. It basically connects the two worlds, you can in a manner of speaking. So you can write the change in length is the deformation tensor multiplied by the change in length in the material particle of, I'm sorry, change in position is related to the change in length. Okay, let me write that here. Relating change in position to change in length of the material particle. Always remember this, the uppercase dx is the change in length of the material particle, whereas the lowercase dx is the change in position with respect to a certain coordinate system. So in for designing or understanding the stress strain relationships in a material, what you want is the true strain or the true change in length. What you get to observe in a measurement is the change in position. How do you relate the two? Through the deformation tensor. So if you measure one, you can compute the other and vice versa. Okay, so today what we are going to see is how do we compute change in area, change in volume. That's the topic for today. So I wrote deformation tensor. The book uses the term deformation gradient, which is a tensor, but the book uses the word gradient, so I'll also use that to avoid confusion. So section 3.4.2, volume changes. Volume changes. Should go with. So if you take any particular point, okay, let's say it is designated by a material particle, the change in volume around that point, dV naught, can be written as, so if you can draw a sphere around that and say that this little point has been deformed by a distance ds, this is equal to 4 by 3 pi ds cube. Consider a point and a small volume around that, by which when you apply a load, it changes a little bit in volume or length in each direction. We write that change in volume. We write the change in volume in terms of a small change in radius or curvature around that point. Okay. So if you write it that way, we need to know what is ds in terms of d lowercase s, the change as seen in the spatial coordinate system. So throughout this discussion, we are going to keep going back and forth between the material and spatial coordinates. So remember that uppercase denotes the material and lowercase denotes the spatial. Okay. So we need to work out this relationship first. Let's think about it. So I told you what is dx, right? Dx we can write is equal to m times ds. How do you think about this? How to think about this? You can write the change in position vector as a direction multiplied by a change in length. A direction multiplied by change in length. So I'm going to ask the question here, basic vector algebra question. Suppose you have a curve, okay, and we say that this curve has a position coordinate s measured along the curve. What does that sentence mean? If a coordinate is measured along the curve. This starting point is s equal to 0. Any other point, if you just walk along this thread, you can say this is L, s equal to L1 or s equal to L2 and so on. Now you are used to measuring distances along a straight line. That is what Euclidean geometry is. We always think, if I say the distance between here and there is 10 feet, without even saying it explicitly, we assume this is the distance I'm talking about. Exactly 10 feet. Now, I might do the same. The distance between 2 points, you can draw the shortest straight line between them, or you can draw any curve and measure the distance along that curve. Okay, this is a similar concept where we say we express the change in position as a vector along which we measure the length multiplied by the change in length. That you okay? Is this making sense? Yes, no? Okay. So we want to first write this, and this dx here is the local deformation. It is localized to a point, so we call it local deformation. And we want to write what is M? Where M is a unit, is a is a is a unit spatial vector that is defined as F times M divided by or normalized by its magnitude. What is uppercase M? Can you extend based on what we have been seeing so far? If this is the direction in the spatial coordinates, uppercase M is a local direction in the material coordinates. Okay, and this F is our deformation tensor. So what we are establishing here is that you can compute the change in length in the spatial coordinate with respect to the change in length in the material coordinate as M ds, sorry, as equal to ds is equal to the magnitude of dx, which is equal to f dot m ds. So ds we call this alpha. Just look at the first term and the third term. And how can you interpret alpha? Just intuitively speaking, forget this for 1 second. What is the quantity ds and what is the quantity uppercase ds? The numerator is the change in position and denominator is the change in length. Material. So what we call this quantity alpha equal to ds over ds is the stretch of a material line element. So we are going to get lots of these formulas, and at least initially it can be a little disorienting. So one suggestion I have for you is, which I'm going to do now, let's keep a list here. Whenever a new formula appears, we'll update that list. And in your notebook also keep 2 or 3 pages for that. Keep updating all the formulas you find in this chapter in one place. Otherwise, later it can become very confusing. Okay. So what is the first formula we saw? Deformation mapping. But let's start our list there. P or x equals P of x. And what is the definition for deformation tensor? That is gradient of x with respect to uppercase x, or this is partial x over partial uppercase x. Okay. Number 3, dx or dxi equal to fij dxj, which is the same as writing dxj is fji inverse dxi, ji transpose dxi. Inverse, just inverse. Okay. Stretch alpha equal to ds over ds which is equal to F dot M. M is a local direction in the material coordinates. What do I mean by local direction? Which specific direction it is? It could be any particular direction you are interested in. So in my example, I told you that if I say that the distance between here and there is 10 feet, I also have to specify along which path. Which path or which direction? Yeah. That is along which direction is it 10 feet? So if I say I draw a straight line between 2 points, it is the Euclidean distance commonly we use. But if you take the globe, for example, and you take any two places on the globe and say the distance if you want to know the distance between them, obviously you are not going to draw a straight line between, say, Mexico and India, because that would the shortest path might pass through inside of the globe. But you already have an understanding that you have to draw that line on the surface only, and that too only where there is or suppose, even getting more technical, it's not just the curve on the surface of the globe, it is a curve which you can actually traverse by ship or plane. It's not any path. You cannot draw a curve through the Arctic and call it the distance between 2 points on a globe. It is a traversable path, right? Likewise, M is a local direction along which we want to know the stretch. Okay, and this direction is chosen by us. It's an input. So F comes from the deformation mapping, whereas M is a choice, right? More clearly, M is a choice, which means you can choose any particular direction. Okay, so we'll keep appending to this list. And we started this because we want to calculate due to a certain deformation described by F. Okay, can you explain that sentence to me? Due to a certain deformation, which is described by F. How can F describe a deformation? What is F? It's the deformation tensor. Of course, it is second order, but it is a relationship between, or it is a sensitivity or a gradient of how the position changes with the material coordinate. So what is F? F is the end result of a loading process, which results in change in shape or change in position, and we express it by F. What we don't talk about is how F is actually affected. What is the loading? We make no reference to that. We just say here is a deformation given by F until the next unit where we talk about loading. Okay. So due to a certain deformation described by F, the volume of a material point or a material particle changes by dV naught. We want a formula or a relation for dV naught. That's our goal. Actually, we want a formula for dV naught in terms of dV, just like we did for the change in length, or change in length. So we'll start by writing a material point at a given position x, and it undergoes a change in volume. And if this radius is approximately ds, okay, first we want to write dv naught is equal to 4 by 3 pi ds. Answer ds. Yes. Did you have a question? Nothing. dv naught equal to 4 by 3 pi ds cubed is the volume of the spherical neighborhood in the material coordinates, or equivalently called reference configuration. That is, this is the reference or the configuration before loading with respect to which we calculate the deformation, right? So this is considering a point and the volume of the element in its immediate neighborhood. Okay. What we want to get is dV. dV is the change in volume in the spatial coordinates or deformed or current configuration. After you apply the load, you take a small volume, which is, let's say, of a very small sphere. Basically, you apply your deformation, this sphere would become like an ellipsoid or a pancake. We want to calculate what is the volume of that pancake. That's the goal here. How to get dV in terms of dV naught. How to get dV in terms of dV naught, or the other way. So dV here, suppose this sphere becomes an ellipsoid. So what you have as a sphere with a radius ds becomes an ellipsoid, and we'll say this ellipsoid has, instead of here you call it radius, here we'll call it half length, dA, dB, and then there's a third dimension, we'll call that dC. Radius, half length. So dV is equal to 4 by 3 pi dA dV dC. Before the math kind of disorients you, can you tell in words what are we considering? We take a point, there is a small volume, spherical volume around that point. You apply your loading, and that is described by F. That sphere, it will obviously deform into another shape, which will look like an egg or an ellipsoid. We are trying to calculate the volume of the ellipsoid. That's the story so far. With me? Good. Okay. I'm I always feel lost sometimes if I don't understand what am I trying to do in this topic. You can easily lose track of what's the next step, because you should keep reminding yourself of your goal. Otherwise, the math can be somewhat disorienting. That is my experience at least. If I write ds squared equal to dA squared plus dB squared plus dC squared, what would you say? Like a local change in length or a local change in distance is equal to the sum of the change along 1, 2, 3 directions. It's almost like writing radius squared equal to x squared plus y squared plus z squared, which is the differential way of writing it. This I know. This I know. Take this relationship. Recall ds is equal to f dot m ds. So if I want ds squared, this is equal to f dot m squared ds squared. Which I can write. So if I write r, sorry, if I take any vector r, it has a magnitude r and a direction r cap. So I can write r squared is r dot r. You know this, right? This basic vector algebra. So I'm going to take this magnitude and write this is f dot m dot f dot m. Which is then written as m dot f transpose times f dot m dv square. The reason it is written this way is to identify a quantity. We're going to call this c squared. Okay. Now recall m is a choice. M is choice, in other words, saying m is an arbitrary direction, and this c squared, which is going to be defined as f transpose dot f. Okay, transpose dot f. This is called the right. I shouldn't say right. I should say right. The right Cauchy green deformation tensor. That is, we are trying to say we'll write this is equal to m dot c squared dot m multiplied by ds squared. Wait, there's no c squared. It's just C is a symmetric second order tensor, second order material tensor. I'm introducing a new word, material. What is F? Let's go back to the basics here. This is like writing Fij is partial xi over partial xj. Take a break. You'll continue writing. So does F belong to the spatial coordinate system or the material coordinate system? It draws, yeah. Somebody was saying. So it draws one basis vector from the spatial and one from the material coordinate system. Look at this quantity, F transpose dot F. If F is defined as F is equal to Fij Ei Ej, what is F transpose? Fji Ei Ej. Can you calculate or can you compute what should be the components of this quantity F transpose dot F? This would be, you write this, say for example, Fji, you already use I and j, you can't use the same thing again. So you will have to write this multiplied by F K J sorry, not FKJ. I'll call this, yeah, FJI, FK, I'll call it L. Okay. That's not how you do it. What is F transpose dot F? So this is, what is F transpose? We'll write it generally Fji, Ei, Ej. With me so far? Dot, I'll have to do F, but I can't use I because I've already used it. I'll write this is F K L E K E L. So this is FJI, FKL. I have EI, EJ, EJ dot EK EL. Question is, should we dot I and K or should we dot J and L? You write this FJI, FKL, okay. If you leave this as EJ, EL, delta IK, or this is FJI, FIL, EJ, EL, or I can replace the dummy index and write this FII, FIJ, EI, EJ. What I did was to do EI dot EK in the spatial coordinate system. That's what I did. What I want you to do is tell me why that is justified. Do you first understand what I did? You are able to, that's not ambiguous. That okay? I had four basis vectors forming a dyad. I had to do a dot product because this operation here is a contracted multiplication which reduces the order by 1. So I'm going to get another tensor where I'm going to get a delta function. That much is clear. Why is this choice okay? Why not do J dot L? That is the question. If we are able to answer that, it means you understand how to do this contraction and it will become easier as we go. See, look at FT. Okay. FT has a certain orientation. It is J followed by I. Same way, F has a certain orientation, I followed by J. So when you're doing a dot product with FT dot F, you are going to have this as the first, and whatever is appearing second is going to be a repeating index. Are you able to piece together how the rules of this multiplication? You are going to do FT, which has the leading direction from the material coordinate and the second direction to be the spatial coordinate. When you do F, the leading direction is spatial and second direction is material. So when you do the dot product, you would be able to eliminate the inner directions because dot product is always first the inner index first, then the outer index. So FT dot F would sum over the second index, which will give you two directions, both of which are in the material coordinate system, making this tensor a material tensor. What is a? There are three tensors that you can now define. F mixed order, drawing a basis vector from one from material system, one from spatial system. A material tensor, which draws both basis vectors from the material direction. We are going to see what is called as a spatial tensor, which would do what? A spatial tensor would have both basis vectors coming from the spatial coordinates. Okay, so let me tidy up this a little bit. Um, consider F transpose dot F. F equal to Fij Ei Ej. F transpose equals Fji Ei Ej. So F transpose dot F involves contraction with respect to the second index of F transpose and first index of F, resulting in two basis vectors for F transpose dot F, both of which are material basis vectors. So you want to keep these notes so that you understand what went on here. So again, yeah, this is okay. So we are going to write in our list. This is stretch. This is 5. C is equal to F transpose dot F, which is equal to Pij Ei Ej and Cij equal to F II multiplied by F Ij. So if you see the second homework, which I may or may not have already posted, all the problems start similarly. They begin by specifying either a deformation or the deformation gradient, and then ask you to calculate different measures or quantities that involve the deformation gradient. Once you have this C, you can use it to calculate the volume change, which we are going to do as the next step. Okay. So why we got here, we started writing ds squared is equal to m dot c dot m ds squared. Now recall, m is an arbitrary direction in the material coordinates or reference configuration. ds is the change in length, or ds is not the change in length, sorry, ds is the radius of the spherical element in the reference configuration. So ds is known. Remember, I told you we start with a small sphere and then observe how the sphere will change shape. So ds is known, m is an arbitrarily chosen direction, and c is calculated from the deformation tensor. All right. So we want to calculate what is dV in terms of dV naught. All right. Now you take C is equal to F transpose dot F. I'm sorry to do this to you, but we did see this in the first unit about quadratic forms. That is, if a tensor can be written as the product of two tensors, and if lambda one, lambda two, and lambda three are the eigenvalues of f. Lambda one, lambda two, and lambda one, lambda two, lambda three are the eigenvalues of f. Then square root of lambda one, square root of lambda two, square root of lambda three are the eigenvalues of C, which is the square of f. And what does eigenvalue itself represent? How do you go back to defining eigenvalues? So if you know that lambda one is the eigenvalue of f, it's like writing any direction is equal to lambda multiplied by the direction. This is the starting point for eigenvalues, right? Eigenvalue is a scalar which projects any tensor, projects a tensor onto a unique direction. I'm sorry, not unique direction, onto a arbitrary direction. Right? So if we write lambda 1, 2, 3 are the eigenvalues of f, then we can write square root of those quantities are the eigenvalues of C. Now where does why is that needed? We talked about the sphere becoming an ellipsoid, each with a half length of dA, dB, and dC, right? So what is the relationship between dA and ds? What is the relationship between dV and ds? What is the relationship between dC and ds? Take a sphere, you deform it, it stretches into an ellipsoid. The scaling this relationship expresses is basically like saying a length changes by this amount in each direction. So if I want to calculate the change in volume dV, this is 4 by 3 pi dA dB dC. This is 4 by 3 pi square root of lambda 1, lambda 2, lambda 3 multiplied by ds cubed. This is dV equal to 4 by 3 pi ds cube multiplied by square root of lambda 1, lambda 2, lambda 3. This quantity is the volume before our volume in the reference configuration, this quantity here. So this is dV naught. So I can write dV equal to square root of lambda 1, lambda 2, lambda 3 times dV naught. What is lambda 1, lambda 2, lambda 3? The product. If lambda 1, 2, 3 are the eigenvalues of f, then lambda 1, lambda 2, lambda 3, nothing but determinant of f. Why? Because any tensor, if it has components f1, 1, 1, 2, and so on, can also be represented as lambda 1, lambda 2, lambda 3, and the rest of the elements being 0. So this quantity here is like writing determinant of f multiplied by dv naught, and we give a special symbol to this determinant of f. We are going to call it j times dv naught, where j is called the Jacobian. J is called the Jacobian, or it's the short form for determinant of f. One more sentence, then you can take that picture. So this dv equals j times dv naught. In the end, this is that simple sentence. Now, keep all of that for a minute. Look at this one sentence which says the change in volume due to a deformation is equal to j times dv naught. And what is j? The determinant of the deformation tensor. Think of some very simple scenarios. What if j equal to 1? No change in volume. It might just work out that how much you shrink in one direction makes up for the expansion in the other direction, so that the net change might be 0. But a very simple case is j equal to 1. That's also possible. That is, if your deformation is nothing but a rotation without any actual change in length, then determinant of f will be 1, which will make this equation dv equal to dv naught. That's one way of thinking about it. In general, think about the process. You have a material sample, you apply load. We don't talk about loading here, but the effect of loading is captured by f. The extent to which determinant of f, or the extent to which j deviates from 1 tells you something. What does it tell you? If j is greater than 1, what is the meaning? Or it's some sort of a tension or an expansion. If j less than 1, it means volume is reducing. It's like compressing more material into the same volume. So, of course, I understand the intervening math is somewhat non-intuitive, but this final equation gives you insight into the nature of the deformation. J, a very simple quantity to calculate. Once you know F, you can easily get its determinant, not a problem. Based on the value of J, you can comment whether it is a volume preserving distribution, or sorry, volume preserving deformation, or it's a deformation that it leads to a compression or expansion. That insight is stored in J, which is the determinant of F. So you wrote C, right? Right, Cauchy-Green tensor. So this is the right Cauchy-Green tensor. The next quantity I would add here, number 6, j equal to determinant of f. J equal to determinant of f, and that connects the change in volume in each coordinate system. Yeah, remove out a few. Can I erase the left side? So here's a question. After doing all these manipulations, what is our goal? Are you able to keep reminding yourself at the end, what is the quantity that matters? What do you think? Which quantity matters in the end? So J is sort of like a intermediate. That is, you get a deformation mapping, like a deformation tensor. You can compute its determinant. If it's one, it tells you something. If it's more than one, less than one, it tells you something about the nature of the deformation. When you are, if you are an engineer, your process almost always is you apply a load and you observe the deformation response of your material. Either you want to specify a load distribution and predict the deformation, or measure the deformation and infer the load distribution. It's either forward or inverse, right? So if your goal is specify the load distribution and compute the deformation, which quantity is the real quantity that you need in the end? Is it dx lowercase, change in length or change in position, or is it the dx uppercase, change in volume, change in area in the material frame? Which is the one that you should really seek in the end?
DX uppercase.
Uppercase. Anybody else wants to say something?
All volume, area, and everything.
In which frame? In the material frame. That is, you take the reference. Always you want to know with respect to that reference, how much has your material changed or your shape changed. The spatial is almost irrelevant in the end. Because the spatial, it's not about the space in which you do the experiment or I do the experiment. It's about what happens to the material. So like you said, finally, it is the dx uppercase or dA uppercase or dV uppercase that matters. And all the manipulation exercises are finally towards that. How do you start with a reference configuration, apply a deformation to that, and observe the change in shape? That's what really is we are doing here. Okay. So now that we talked about volume, let's talk about area changes. Area changes. Okay. So consider dx and dy, two material vectors, dx and dy. You can calculate what is dx cross dy. So going back to some basic vector algebra, if you have A and you have B, what does A cross B represent? A cross B is the area of this vector. I'm sorry, A cross B is the area of the parallelogram formed with A and B as adjacent sides. Adjacent sides. And you would have learned this in high school. We use what is called as the right hand rule to say that if you have A and you rotate by an angle theta in the counterclockwise direction, you get B. The orientation of this vector should be drawn as a vector that is coming out of the board. So A cross B represents this area. And if somebody asks you if this area is a scalar or vector, what would you say? It is a vector. This area, it's weird that in geometry, a point is a scalar, a volume is a scalar, but length and area are vectors. That vector is defined with a magnitude equal to the area of this parallelogram and a normal vector that is pointing this way. So when you write A cross B, this is A cross B equal to, I'll write it dA multiplied by dA cross dB. And this dA is the area of this parallelogram. Okay, so when we write dx cross dy, we can write this is equal to a normal vector multiplied by dA naught. I could have just written this. I could have just said dx cross dy is represented by a vector multiplied by the magnitude of the area. I just wanted to connect with something that we all know from, undergrad or high school. So you have, let's say you have two directions, dx, dy, and it represents an area dA naught vector. Okay, and that dA naught can be written as dA magnitude multiplied by n cap. And n cap is not some arbitrary thing. N cap is dx cross dy divided by the magnitude of dx cross dy. All right, I'm going to read a sentence from the book, which has been kind of reinforces what I'm saying, what I've been saying. This is page 80. As a result of the imposed deformation, characterized locally by the deformation gradient f, material vectors dx uppercase and dy uppercase are mapped to the spatial vectors dx lowercase and dy lowercase of the deformed configuration. For this entire material sample, f is our deformation tensor. You can write dx is equal to f dot dx and dy equal to f dot dy. This is what I've been telling, right? A loading creates a deformation. Deformation is described by the deformation tensor. It connects a local change in dimension, which is dx uppercase, to a spatial change in length, which is dx lowercase. That's what this statement is. So I really ask you to go back and look at page 80. It's at the tail end of the page where you can see this sentence, okay? dA naught area in the reference configuration. dA area in the deformed configuration. dA is equal to, dA not equal to n cap dx cross, n cap is equal to dx cross dy, which you can write n cap multiplied by dA naught. dA is equal to dx cross dy. That is the area in the deformed configuration is again the product of the two deformed vectors. So now express dA in index notation. So DAI is equal to dx cross dy ith component. Means what is this? This is DAI EI. Right? So what is dxi? Sorry, dx cross dy I component. Again, reminder, if A is equal to AI EI cap and B is equal to AJ EJ cap, what is A cross B? We saw this when we did the first unit. A cross B would be AI BJ EK epsilon IJK. Right? This is same as writing I J K AI sorry E1 E2 E3 A1 A2 A3 B1 B2 B3. Right? This is the expression for cross product in determinant form and index form. So this is nothing but this is the ith component of the cross product. So this must be dx j cap dy k cap epsilon I j k. Look at it and tell me if that makes sense to you. See, this here is A cross B, the kth component. That's why we multiply by EK and add the permutation symbol. Actually, I should write it as epsilon ijk multiplied by EK. So if I want the ith component, ijk, they are all just labels, right? Dummy index. I'll call it dxy dyk multiplied by eijk. This would be the ith component of dx cross dy. So I'm going to write you want to take a picture before I erase it fully? So I have DAI equal to dxj dyk epsilon ijk. The goal is always wherever you get spatial representations, convert them back to material representation. So what is dxj? How can you write it in terms of the material coordinate system or the material vector dx upper cap?
D upper cap.
Okay.
Small divided by
F
G small capital.
right? F J J, or if you are not very comfortable saying that, F J K dxk. And then we'll write, actually, let's keep the J, even if it's a little uncomfortable. And then dyk is F K K dxk. So my DAI would be FJJ FKK epsilon IJK dxj dyk. This is nothing but DAI. Okay, keep that in. If I write DA is equal to NI DAI NI sorry N cap DA sorry N cap DA. This is DAI EI. Okay, missing something here. Okay. So this I'll write as N cap DA, which is NI EI cap DA. Or if I compare this expression and this expression, I'm going to get DAI, nothing but NI DA. DA is a scalar, DAI is the ith component of the vector DA. Okay. So what is my DAI? I'm sorry, what is my DAI? That's right. What is my DAI? That is F ij F K K epsilon ijk dxj dyk is equal to ni dA. So it does make sense. There is j, there is so lowercase j and k will go away because they are repeating indices. The summation will take care of them. There is jk, there is jk. So that the uppercase will also go away due to summation, and you're left with an I, left with an I. So it's consistent. Okay. How do we eliminate the I? If you want to turn this into an equation for something that doesn't involve I, but something that involves the material vector, what will you do? You have Ni. I want to go from Ni to Ni. What should I do intuitively? If I multiply this by Fii, wouldn't I get something that is in the material system? Because by summation, this will go away. I'll be left with the material vector. So this is essentially a transformation between, if I write x equal to f dot x, I can also write n cap is equal to f dot n. That's exactly what I'm doing. Okay, so we multiply both sides by Fii multiplied by Fii. Almost there. Okay. If I multiply by Fii, what am I left with? So I have epsilon ijk fii fjj fkk. This is nothing but determinant of f or j multiplied by dxj dyk. And this is equal to ni fii, which is uppercase ni times dA. Okay. I'll stop this here because there are two more steps and you will feel rushed if I do it now. What I'm going to do next week is I'm going to pick it up from here. Next week meaning Thursday, or sorry, Thursday's exam. We'll pick it up here after the break, after the spring break. Now it's almost time, but let me quickly talk about the exam. On Thursday, 80 minutes, you saw the mock exam, 3 problems. You can almost assume that each problem will be a template in the 3 problems that I gave. If third problem is prove an identity, third problem will be prove an identity in the exam also. If fourth question is a qualitative question on chapter 1, it will be a similar question on the exam also. So there will be one problem related to finding eigenvalues and eigenvectors, one related to proving identities, and one related to manipulating tensors or identities. That is one related to manipulation of tensors, one related to the last topic, tensor calculus, that is gradient, divergence. One problem will involve that. Okay, so open book notes, you can bring whatever material you want, including your past homework and everything. 80 minutes, please be on time. Any questions?
Any way we can get our homework back?
Sure. You can see, you can pick it up tomorrow from my office. I'll be here by noon. Between noon to 4:30, I'll be in my office. Come get your homework. Yeah, tomorrow also, if you have any questions, please come by. On Thursday, I have a doctor's appointment at 2 o'clock. I plan to reach campus only by around 3:30. So if you are coming or planning to come, 3:30 to 4:30 or 3:30 to 5 will be a good time if you have any questions. Okay. In any case, email me. Okay. Thank you.